Hi everyone. Good evening to one and all present here. This is going to be the seventh weekly live session of the NPTEL course of Remote Sensing Principles and Applications. This is brought to you by NPTEL and the Swayam Initiative. I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme at the Interdisciplinary Center for Water Research, IISc Bangalore, in IISc Bangalore. And this course has been tutored by Professor Ishwar Rajshekharan from the Department of Civil Engineering, IIT Bombay. So first things first, just the common information about each live session. The video recording of the sessions will be made available on the YouTube channel. Number two, the files relevant to the sessions will be made available through a Google Drive folder. Number three, the files and the video recordings will be made immediately available after the class. And number four, if I've taken any image from the internet, they're not for copyright infringement. They're solely for educational purpose. So far we have gone through 6 weekly live sessions. So far we have gone through 6 weekly live sessions, and I have already uploaded the recordings of each of the weekly live session on the YouTube channel. The link of which I've already shared with you, and this is the link for the Google Drive folder, in which I am actually uploading the illustrations of these weekly live sessions. Today we are going to discuss about the brightness temperature prominently, and we would be putting more focus on the Planck's law and Planck's function, and how we arrived at an approximation of the Planck's function in the form of Rayleigh-Jean's law. That is what we will be discussing today. So today's session has a lot to do with radiometry basically. Please give me 1 minute. So we would be solving only 2 questions today, but we would be solving a lot more theoretical concepts. So some of the questions I have not actually written here in the slide, but I will be discussing it with the codes, and there's every possibility that these questions may actually come in some form or the other in the main examination also. Yeah. So the first question to be discussed today is about but before starting the session for today, just a brief about what I'm going to discuss today. I would be again putting some light on the 3 fundamental laws, namely the Planck's law, the Stephen-Boltzmann law, the Wien's law, and something new which was discussed only in the previous week of the course, namely the Rayleigh-Jean's law. And we would be discussing how this arrived and what can be its implications. We would also be discussing a bit about the brightness temperatures. We already solved a question of brightness temperature for Landsat, based on the fundamentals of the Landsat handbook in weekly live session 2 or 3, if I'm not wrong. But we would be dwelling into a lot more detail of brightness temperature today. We would be understanding how brightness temperature is different from, let us say, the thermal temperature, and this is how the second question actually arrived. And apart from that, there would be a lot more basic conceptual understanding today based on these 2 concepts. So the first question today is which law approximates the spectral radiance of an electromagnetic radiation as a function of wavelength? Okay, so the laws are Rayleigh-Jean's law, B, Stephen-Boltzmann law, C, Wien's law, and D is the Lenz law. Okay. We know very well that Wien's law is basically a very special case of Planck's law. Stephen-Boltzmann case is also a special case of the Planck's law. Rayleigh-Jean's law is also a special case of Planck's law. Lenz law has nothing to do with our part of the remote sensing which we are considering. It is something to do with magnetism, by the way. So yeah, so it has to be either one among part A, part B, or part C. So all these, the fundamental law is the Planck's law itself, the Planck's function itself, from which all of them actually arrived. All these 3, laws actually arrived. So we have already discussed the derivations of Stephen-Boltzmann law and Wien's law in one of our earlier weekly live sessions. The answer to this question is, by the way, the Rayleigh-Jean's law. But I will be discussing how it arrives and where you can use it. You cannot use it everywhere because As it is clearly stated, it is just an approximation. It is not a fundamental law which you can use everywhere. You can use only the Planck's law everywhere, but you cannot use the other laws at every single mathematical formulation you design. So let's discuss it now. So this Rayleigh Jeans law is the answer. First of all, it is, as the name suggests, it is an approximation to the spectral radiance, and you know very well that Stephen Boltzmann law as well as Planck's law also have to do with spectral radiance of electromagnetic radiation as a function of wavelength from a black body at a given temperature. Okay, so it has something to do with the temperature and the wavelength. So these are the two variables of this Rayleigh Jeans law, and let me just give the expression first of all. We will derive it in due course of time. Please give me just half a minute. Okay, so the Rayleigh Jeans law has to do with the wavelength and the temperature, and the expression is, again, it calculates the radiance itself as a function of temperature, that is by T, which is equal to 2C kB T by lambda power 4. So it is basically inversely proportional to the fourth power of the wavelength. And C is the speed of light, you know it very well. We have used it umpteen times already. Kb is the Boltzmann constant, which is a fundamental number, fundamental constant. And yeah, so that is it. And T is the absolute temperature in kelvins. We never use Celsius while putting into equations in this part of the course. Okay, so B lambda is the spectral radiance. Spectral radiance, which is in descriptive terms the power emitted per unit emitted area per steradian per unit wavelength. So its unit would be watts per meter square per steradian per micrometer or per meter, whatever way you want to describe wavelength. C is the speed of light, which I have depicted here. Kb is the Boltzmann constant, and T is the absolute temperature. Temperature or absolute temperature is nothing but the temperature in kelvins. Okay, so this is the term for Rayleigh Jeans law in terms of wavelength. Lambda. Now what happens is that when you move into let us say microwave remote sensing framework, okay, so when you move into the microwave remote sensing framework, we usually refer to the frequencies rather than referring to the wavelengths. So what happens is that we need to have a similar we need to convert this wavelength formulation of the Rayleigh Jeans law into the frequency formulation of the Rayleigh Jeans law. Let's see how it arrives. Now one thing to think about. Sorry for that. Yeah. So we have B lambda T. We have B lambda T. We want to reach B nu T, where nu is the frequency. So how can we reach that? When B lambda T is already 2C kBT by lambda power 4. 2C kBt by lambda power 4. So how would we arrive at b lambda b nu to the power t? I mean, we would want to relate the radians in terms of frequency. So how do we do that? So do we use the fundamental, I mean, do we just convert lambda to frequency using c is equal to nu lambda and get into a term for b nu t? Do we do that? It's a food for thought. No, we don't do that. I will tell you why we don't do that. I mean, this would have been the easiest way to do. To convert the wavelength form of the Rayleigh-Jeans law into the frequency form of the Rayleigh-Jeans law, but we cannot do that, and that is for a reason which I am going to discuss. I think 10 minutes from now. Okay, so we will discuss that. It would have been very easy to substitute lambda as equal to c by nu and get into the frequency uh, form of the Rayleigh-Jeans law, but no, that is now how it works. Currently, I will just give you the formula for the frequency form of the Rayleigh-Jeans law, but I will derive it also in today's session itself. The formula is 2 nu square kBt by c square. This is the actual formula. This does not arrive from this formulation at all. Okay, this is the frequency form. Frequency form of, and frequency form we usually use in microwave remote sensing purpose, where the wavelength has become too large, so we rather discuss things in terms of frequencies. Frequency form of Rayleigh-Jeans law. Okay. Now another thing, I will be coming into the derivation in just a few moments from now, but before that, the assumptions. Why is it known as an approximation? Why is it not a fundamental law like the Planck's law? Because Planck's law can be used everywhere, but not Rayleigh-Jeans law. So the Rayleigh-Jeans law agrees with experimental results at large wavelengths or low frequencies, but disagrees at short wavelengths or high frequencies. And this disagreement is also commonly known as the uh, ultraviolet catastrophe. This is what this disagreement is known as. Okay. So there are some places, specific location or the specific bands of wavelength or frequency where you can use this approximation, because it does not agree well with the experimental results, unfortunately. Now let's go into the derivation, and this derivation is very easy, but this derivation is also important to understand why and how we should be using this law. And as every law which I have discussed so far, the fundamental laws of the Wien's, the laws of Wien and the Stephen Boltzmann law which I have discussed, this law would also emanate from the Planck's formula itself, Planck's function itself. So let's try it out now. Okay, now let's try to compare it with the Planck's law. Planck's law we know is this 2hc square by lambda power 5 1 by e to the power hc by lambda kBt minus 1. So this is the Planck's law. We know it very well, and this is applicable for black bodies. Means a perfect emitter. So I mean there are a few constants here. H is the Planck's constant, and Kb is the Boltzmann constant. And b lambda t in some textbooks is also represented as L lambda t. So please don't get confused. I mean by the notations. Okay. So now let's do one thing. We need to simplify this denominator term, this exponential term somehow. And the best way to simplify exponents is basically the Taylor's approximation. So Taylor's approximation, if you just revise, it just converts any sinusoidal function or exponential function or any transcendental function into a list of polynomials. That is what we will do with this thing also. We need to convert it into some easier form. So let's do that. Now e to the power x, I mean if we convert it into a polynomial form thanks to Taylor's function, it would be 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So this is the Taylor's series. This is thanks to the Taylor series approximation. So Taylor series is a way, or it's a tool by which we can convert any function into some set of or some list of polynomials. So let's look at the limit. In limit, if high temperature is in the denominator of the exponential term, okay, lambda is also in the denominator of the exponential term. If high temperatures or long wavelengths the term in the exponential becomes small. I mean nothing called rocket science here. If the denominator is increasing, then the overall term will be diminishing. Okay, so let me take another slide to get into that. It's a very easy derivation, by the way. So hold your cards just a few minutes more. So this was the exponential term. If t increases or if lambda increases, then the entire term will decrease. Exponential, if this is inside term, so this inside term will decrease, resulting in an exponential term will to decrease, because exponential functions are increasing in format. I mean, if the thing which is inside the exponential bracket, it increases, then the exponential function will also increase. Okay, because it's an increasing function. Okay, so let's take that out. Now let's approximate it with Taylor polynomials first order term. So we already saw in the last page that e to power x is nothing but 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So if x becomes too small, which is what would happen if lambda and t becomes too large, then we can just take e to power x approximately as 1 plus x. We did not go into the higher order terms actually, because the higher order terms will actually tend to 0. Or will be almost negligible when you compare it with x. So that is what we will be doing here. So exponential of hc by lambda kt is 1 plus x, and x in our case is hc by lambda kbt. That's it. Now let's take the let's take this term. Okay, so this dotted thing, let's consider that now. So 1 by exponential hc by lambda kbt minus 1 would be nothing but would be nearly equal to, these are nearly equal to, they are not strictly equal to, okay. So 1 by, this is 1 plus hc by lambda kbt minus 1 again, so 1 will get cancelled out, so it will be 1 by hc by lambda kbt or lambda kbt by hc. That is what we get from this expression after the approximation, okay. So the Planck's law now will get reduced to Planck's black body law, black body formula. Now gets reduces to b lambda t equal to, it was earlier 2hc square by lambda power 5, okay. So this thing will still stay intact, 2hc square by lambda power 5, this is as it is. And what did we approximate this exponential 1 by exponential term to? It is basically lambda kbt by hc, lambda kbt by hc. So we are left with b lambda t is equal to 2c kbt by lambda power 4. So this is how we arrive at the Rayleigh Jeans formulation. Rayleigh Jeans formulation or expression. Okay. So this is again mind you, this is the wavelength form of the Rayleigh Jeans formulation. We also discussed about the frequency form of the Rayleigh Jeans formulation. Where was it? Yeah. So this is the frequency form of the Rayleigh Jeans formulation. And you would be minding, I mean, from this, why didn't we come to this? I mean, why didn't we just use C equal to nu lambda? Because C equal to nu lambda is also a fundamental expression. Why didn't we use that to come into the frequency form of the Rayleigh Jeans formulation? How did we arrive at this? We will discuss this also now. And based on that, we will solve some questions, which I have not written here actually. But yeah. Now let's apply the same to the black body radiation expressed in terms of frequency. Frequency is nu is equal to c by lambda. I mean, this is the fundamental. Now in limit of frequency, that is h nu will become much lesser than kbt. B nu t will be written as 2 h nu cube by c square. So someone is trying to enter, I believe. Times kbt by h nu. So we arrive at 2 nu square kbt by c square. So this is the Rayleigh Jeans formulation in terms of frequency. And this is what I discussed there. Now still, I mean, that doubt is still not solved. I mean, why don't we just substitute c equal to nu lambda to the wavelength expression and arrive at a frequency expression of the Rayleigh Jeans approximation? Why don't I do that? Why are these two expressions so inconsistent? So let's think over that. Let's proceed. I mean, let's try to solve that mystery. are the frequency form, frequency means nu, form and wavelength form of Rayleigh-Jean's uh, law consistent? Are they even consistent with each other? Because they're definitely not following a very fundamental relationship between the frequency and the wavelength of electromagnetic radiation, that is C equal to nu lambda. So are they consistent? They in fact are very consistent, and I'm telling you why. I'm actually going to write the reason behind the consistency. B lambda t is actually the first. It's a differential of the power emitted by the body. So dp by d lambda is b lambda t, which is actually the wavelength form of the Rayleigh-Jean's approximation. And dp by d nu is b nu t. Okay. So it is very clear now that b lambda t and b nu t will not have the same units, and hence they are not strictly equivalent. Okay. Even after substituting c is equal to nu lambda. Okay. Because b lambda t has units of, they have separate units, has units of energy emitted per unit time per unit area of emitted surface per unit solid angle per unit wavelength. So the per unit wavelength is important in b lambda t. It is per unit wavelength and whatever the thing is above. Okay. Whereas b nu lambda is basically whatever the thing is above per unit frequency. So these are basically nothing but different outlooks to look at it. Look at these two formulations, the frequency formulation and wavelength formulations, are just the two different outlooks to look at this energy balance. And we will be trying to do an energy balance formulation also just a few moments from now. Okay. Let me just write it up for b nu lambda 2, b nu t also. Okay. b nu t has units of energy emitted per unit time per unit area of emitted surface per unit solid angle, that is in steradian, per unit frequency. So this is the difference. The units are not same of b nu t and b lambda t. Okay, so b lambda t, the thing is all same till the end. So it is per unit wavelength, the b lambda t, and b nu t is per unit frequency, and that is why we cannot straight away substitute it, because the things are not equivalent as such. Okay, now let's try to be consistent. How to bring a consistency? In the wavelength and frequency formulations. As such, they are not consistent. That is what we found out. The units are different, and that is why we could not straight away substitute c equal to nu lambda. But how to bring about a consistency? Okay, so the thing was that dp by d lambda. Let's just go back to the basic formulation. Was equal to b lambda t, and dp by d nu was equal to b nu t. Okay. So how do we bring about a consistency? Let's just equate dp at both the sides. So we will get b lambda d lambda. I'm just not writing b lambda t and b nu t for the sake of some conciseness. Equal to b nu d nu. Okay. This is fundamental again. Now both sides now have units of power. Units of power, or power is nothing but energy emitted per unit time, joules per second, per unit area, per unit area of emitting surface, per unit steradian or solid angle. That's better. Okay. So now b lambda d lambda is equal to b nu d nu. We have brought about a similarity of the units. So now they would be consistent. So let's bring about the consistency and look at it a bit deeper. Keep. We'll take just one more slide to finish this formulation. So b lambda d lambda was equal to b nu, or b lambda t d lambda was equal to b nu t d nu. Okay, this is what we got from the previous one. So we can also get b lambda t to be equal to b nu t d nu by d lambda. Just took it there. Okay. Now d nu by d lambda is something which we can find out. It would be equal to d by d lambda by c by lambda, because c is equal to nu lambda, and it's a fundamental thing. Okay. So nu can be written as c by lambda, and that is what we substitute here. So this would become equal to minus c by lambda square. So d nu by d lambda is minus c by lambda square. Let's substitute it there now. So b lambda t will become 2 kbt c by lambda square by c square times c by lambda square. So this is nothing but 2c kbt by lambda power 4. And that is how we got into the wavelength formulation. Again, these are the radiances. Now what I mean, for a black body. Now what happens if that is not a black body, that's a gray body? A gray body is something which has an emissivity less than 1. For a black body, we know that the emissivity is exactly equal to 1. So what would happen in that case? Let's look at it now. Let me take another slide. So we from the last one we got b lambda t. How do we get? Let us suppose we are measuring the radiance at a point. How do we get it? B lambda t was something 2c kbt by lambda power 4. Okay, that we found already. Now how do we get into the measured value? The measured value of a particular surface will contain a signature of its emissivity, because the emissivity of a black body is exactly equal to 1, but no ideal body is actually, I mean, no real life surface is actually a black body. Okay, so it will have some emissivity which is usually less than 1, between 0 and 1. So you just need to multiply it with the emissivity epsilon 2 C kb T P by lambda power 4, where Tp is the physical temperature of the surface. Okay, so this is the end of the Rayleigh-Jeans law for today. But again, I mean, we learned a lot of things. We first of all learned that we cannot use it everywhere. It is only consistent at a particular wavelength range or frequency range. Okay. Uh, so whenever lambda becomes very high, the wavelength becomes very high, we can easily omit the third parts. I mean, these higher order terms in the Taylor series expansion of the exponential term, and hence we can reach to Rayleigh-Jeans formulation from Planck's law. That is what we did. So Rayleigh-Jeans law is useful only for a particular type of formulation. Now, in today's session itself, we will also be discussing about the something known as the brightness temperature, and brightness temperature also comes from radiances itself. So if we had to use the Rayleigh-Jeans formulation, I mean, brightness temperature, if you don't know, comes from inverting the Planck's law. Okay, and if you use the Rayleigh-Jeans formulation itself, the brightness temperature would have been Tp. You just had to invert this to get the brightness temperature, but that will not be valid over all the wavelength ranges, and hence brightness temperature is usually found out for all the wavelength ranges only. That is by inverting the Planck's law. Okay, let's do that now. Now the next question is, can the brightness temperature be measured with a thermometer? Okay, so a few things we need to understand. Number one, what is a brightness temperature? I already discussed that brightness temperature comes when you invert the Planck's law. Okay, and you basically segregate the temperature term. In that case, that temperature term, the segregated temperature term, is nothing but the brightness temperature. So it comes from radiances. And what does the thermometer measure? Does a thermometer measure radiances? I mean, how does it give you the temperature? Is it by measuring radiances? So no, I mean, a thermometer does not work like I mean, work by measuring the brightness temperature. It only measures the thermal properties. Okay, so let's write it down. Brightness temperature is the measure of temperature of a radiating body in space, such as any celestial body, let us say a star or sun, such as star or a planet, based on intensity of its electromagnetic radiation at a particular frequency. And another point to be noted is that this is not related to the temperature that a thermometer would measure. A thermometer, on the other hand, only it is only designed to measure the temperature of a material by detecting thermal energy that it contains. Okay. Now, the brightness temperature depends on various factors such as distance from the sun, albedo of the surface, or temperature of atmosphere. Okay. Also, brightness temperature is inherently, because it comes by inverting the Planck's law, brightness temperature is inherently a function of wavelength or frequency. So let's try that exercise now. How do we invert the Planck's law to get into the brightness temperature? Let's try it out. So the Planck function is like this: b lambda t is equal to 2hc square lambda power minus 5. I'm not writing it in the denominator for the time being, times e to the power hc by lambda kt minus 1. This is the Planck's function. And unit of b lambda unit would be joules per meter cube per second per steradian, or equal to watts. Joules per second is watts per meter cube per steradian. Okay. Or watts per meter square per steradian per micrometer. There are several ways of writing the units of b lambda. Okay. So it will vary. Now let's take this term hc by lambda kt and denote it as beta. Let this be hc by lambda kt. Now let's compute emitted radiance from temperature. Say the temperature be minus 60 degrees Celsius equal to 213 Kelvin. So what would be the radiance? So lambda would be, let us say, 10 micrometer, which is nothing but 10 into 10 to the power minus 6 meter equal to 10 to the power minus 5 meter. So let's find it out. So let's compute beta now. Beta was hc by lambda kt. H is 6.64 into 10 to the power minus 34 joules second. C is 3 into 10 to the power 8 meter per second. Lambda is 1 into 10 to the power minus 5 meters, 10 to the power minus 5 meters. K is Boltzmann constant 1.38 into 10 power minus 23 joules per Kelvin, and T, the absolute temperature, is 213 Kelvin as we took in the problem. So it was minus 60 degrees, it is equal to 213 Kelvin, because we only put absolute temperatures here in this chapter. So this comes out to be 6.77. Okay. Now B lambda T would come out to be 6.63 into 10 power minus 34 joules second, 2 hc square into lambda power minus 5 by this thing, exponential minus 1. So 3 to the power 10 power 8 meter per second square into 10 power minus 5 meter hc square into lambda power minus 5 by e to the power 6.77 minus 1. So it is 119.3 into 10 power 7 by 870.3, which is equal to 0.137 into 10 power 7 joules per meter cube per second per steradian. Okay, or 1.37 joules per meter square per second per steradian per micrometer, because usually that is what we write it as. Now joules per second can also be written as watts, by the way. So yeah, this is the fundamental unit. Now what kind of problems can come in this part? So problems would have a range of wavelengths, say centered around 10 microns, 10 micrometers. Okay, let's say it would be a range. Okay, so the spectral resolution is a length, it's a range, it's a bandwidth. So let us suppose it is 8 to 12 micrometers. Okay, the centered, it would be centered around 10 micrometers. It is very easy to understand. So the wavelength increment equal to delta lambda equal to 12 micrometer minus 8 micrometer, it would be 10 micrometer. Sorry, it would be 4 micrometer, 4 into 10 power minus 6 meter. We are converting the micrometers into SI unit, that is meters. Now consider a solid angle increment delta omega equal to 10 power minus 4 steradian. Consider a square emitting area with dimensions 2 meter by 2 meter, which is delta A, written as delta A, is 4 square meters. Okay, so the power emitted would be B lambda T times delta lambda delta omega delta area, because it was per wavelength, per steradian, per solid angle, per cross section area. So that is why we are doing it, per area. So that is why we are doing it, surface area. So that is what we are multiplying it. So let's do it in the next slide. Yeah. 137 into 10 power 7, 4 into 10 power minus 6, 10 power minus 4 times 2 equal to 2.192 into 10 power minus 3 watts, the powers, or 2.192 into 10 power minus 3 joules per second, since 1 watt equal to 1 joules per second. So we can convert. Now the next part would be computing temperature from observed radiance, which is also known as the brightness temperature. Okay, so let's do it now. So substituting the observed radiance, T is equal to 1438.8 by ln 119.1 by 0.5. I'm just substituting the value which we found already. Okay, so it's not like I'm doing it for the first time. It comes out to be 1438.8 by 5.477 equal to 262.6 kelvins. Okay, and 262.6 kelvins is around minus 10 degrees Celsius. Okay, so our estimate of the surface temperature, our estimate of the surface temperature is 262.6 Kelvin, which is equal to minus 10.5 degrees Celsius. And what did we start with? We started with some particular temperature. It was minus 60 degrees Celsius, and our estimate from radiance assessments is basically minus 10.5 degrees Celsius. Okay. Now, had we used I lambda equal to 0.137 into 10 power 7 watts per meter cube per steradian, we would have recovered the temperature. We would have recovered the temperature used in the previous example. That was T is equal to 213 kelvins. That was minus 60 degrees Celsius. Okay, so you need to put a more accurate estimation of the radiance to get into it. So what did we do? We rather than that, we chose a higher radiance, and that higher radiance resulted in a higher brightness temperature. Okay, the higher brightness temperature in our case came out to be minus 10.5 degrees Celsius instead of minus 60 degrees Celsius. So the higher radiance gave higher brightness temperature. Okay, so let's see that now, and let's try to come to the derivations of how we arrived at it. Assume I lambda is equal to 0.5 into 10 power 7 watts per meter cube per steradian. Okay, in the thermal infrared window centered around lambda is 10 micrometers. So the denominator of Planck's term is nothing but e to the power hc by lambda kbt minus 1, or kb we will write just as k. Okay, so it will be 2 hc square times lambda power minus 5 by I lambda. Okay, we're just trying to segregate temperature. Okay, so this is the Planck's law. This is the denominator. This is the another form of Planck's law. We're just writing the same thing, but we have actually taken the denominator to the left hand side. That's what we have done so far. Now take the logarithm of it. Hc by lambda kt is equal to ln 2 hc square by lambda power 5 I lambda plus 1. Okay, this implies T, just invert it to get the temperature, the equation. Hc by lambda k times 1 by ln 2 hc square times lambda power minus 5 by I lambda plus 1. That is how we arrived at this. Now let's just define these two terms. Okay. Define the factors. K1 would be 2 hc square by lambda power 5, which is nothing but the ln term, and K2 is hc by k lambda. K2 is hc by k lambda, which is this term. Okay, so the inverted Planck function would look like T is equal to K2 by ln K1 by lambda plus 1. And this is what is given in the Landsat handbook also. Now for given wavelength, say lambda is equal to 10 power minus 5 meters, K1 would arrive as 119.104 into 10 power 7 watts per meter cube per steradian, and K2 would be 1498.765 Kelvin. You don't need to worry because these values are already given in the MODIs as well as Landsat handbooks. Okay. If you want to arrive at the brightness temperatures. So let's just put the values and then we will get T is equal to 14398.8 by ln 119.1 by 0.5 plus 1, and this is 262.6 kelvins. Okay, and this is minus 10 degrees Celsius, around minus 10 degrees Celsius, and it's actually a bit higher than the actual temperature which we considered. The actual temperature considered was minus 60 degrees Celsius, which was around 211 Kelvin. So it's a bit lower, higher than that. Why is a bit higher? Because the radiance has actually increased. If the radiance increases, then the brightness temperature will also increase. That is what we understood from it. Now let's look at the units. Often the radiance is given in units of watt per meter square per steradian per micrometer. Okay, this is the one which it is generally given in. It may also be given in watts per meter cube per steradian. It may be also given in joules per second per meter cube per steradian. It may be even given in joules per second uh, per meter square per micrometer per steradian. So there are several ways of representing this thing. So always, whenever this question comes in the exam, always check the units of K1 and K2. And if they are not given as such, then just assume that it is in watts per meter square per steradian per micrometer itself. Okay. Okay. So this implies the values will be 10 to power minus 6 times smaller because the conversion of meters to 10 micrometers, and K1 must be divided by 10 power 6. Now let's look at the values of K1 and K2, the constants for some of the bands of some very common sensors. One Landsat sensor we will look at, which is the enhanced thematic mapper ETM, and one MODIS sensor also we will look at. Values of K1 and K2 computed for specific sensor bands. Let's just tabulate it for the time being. So these are the sensor. This is the band, a range of wavelengths in micrometer in our case. Where is it centered at? Because that centered wavelength is also what we use. Then K1 multiplied by minus 10 to the power minus 7. I mean, that is what we will write it as. Then K1 in terms of micrometer, and K2 which is in kelvins. The first one, the one example which we took, in that the center was 10 micrometer, which we already took. The K1 value comes out to be 119.104 into 10 power minus 7 micro. So if you convert it into micrometer, 1191.04, and K2 in kelvins comes out to be 1438.765. So that was the example which we took. Now enhanced thematic mapper plus, a very famous sensor by Landsat. Let's look at its band number 6. The range is 10.4 to 12.5 micrometers. 11.45 would be its center. 60.51. The values I'm just putting. 1256.6. You will get these K1 and K2 values in the Landsat handbook, by the way, which is in the USGS website. Then MODIS, band number 31, 10.78 to 11.28, 11.03, 72.957 would be K into 10 power minus 7 would be K1, 729.57 K1 in micrometers, 1304.4 K2. Another MODIS band 32, 11.77 to 12.27. It would be centered around 12.02, 47.471, 474.71, and this comes out to be 1197.0. So this is how we got to know how these values of K1 and K2 arrived. Now just one thing, these values 605.1 and 1256.6, in USGS they are instead written as 660.09 and 1282.7, because they have not chosen the center as 11.45, but they have chosen the center as 11.22 micrometers. Otherwise, they all are same. That is how we arrive at. So far we were discussing about black body radiation only. What if the body is not black? I mean, what if it's not a black body? So non-black body radiation, non-black body radiation. So they will emit less than the than what the Planck function predicts, because Planck function is for black body. Okay, so I lambda in that case would be E lambda epsilon lambda times B lambda. Epsilon is the emissivity. And it is from 0 to 1 for a non-black body, and epsilon lambda is equal to 1 for a black body. So the inverted Planck function becomes, for a non-black body, T is equal to K2 by ln epsilon lambda, which is the emissivity, K1 by I lambda plus 1. So this is the inverted Planck function. So this epsilon term actually came here. That's the only difference. Now, in the previous example which we took, example with I lambda equal to 0.5 into 10 power 7 watts per meter cube per steradian, centered at lambda is 10 micrometer. If we took epsilon equal to 0.95, we would get T is equal to 265.06 kelvins instead of T is equal to 262.6 kelvins. So we conclude that to emit the same radiance with a lower emissivity requires a higher temperature. That's it. I think we are done for the day. So let's call it for the day. And we'll meet again in the 8th weekly live session. But we discussed a lot today. Whatever was left, from my part, in terms of the brightness temperature, that is now over. From the live session, we will concentrate on the microwave remote sensing.